Okay, here are some corrections that we can make to boost our grade. I'm going to be taking these corrections and applying them to an old quiz grade. But in order to do that, you have to really do these problems correctly and show me that you have an understanding or a better understanding of limits and how to evaluate graphs. So for this problem right here, we see that we have two different types of problems. We have the limit as we approach -2, and then we just have kind of what is the value at -2, and the same thing for -4. Now, some things that you need to remember about limits is limits really mean as we approach. So this is like the limit as x approaches -2. So this is going to be as we approach, or as the function approaches -2. Okay, so the word approach is in there because what that means is like what we are getting close to. And one hint for me on limits is going to be to really follow the graph. Okay, so follow the graph in order to find my limit, right? So kind of tracing over that graph in order to get there. There's no jumping around, it's really just follow the lines. So from the left of -2, let me do this in red here. Let's see, let's annotate where -2 is. That's right here. So there's my x value. And so from the left of that, I'm going to draw that in red. We are approaching some value -1, right? So I'm just going to temporarily put that in there. And then I'm going to check also from the right of -2. So if I follow the graph from the right of -2, okay, and we stop at -2, we can see that basically the graph approaches, or is, as one student said, joins together at that -2. Now I know that there's a little hole, something missing there, but we don't care about that. Where is our graph going? Where is it headed? Where is it approaching? And from both sides, it's approaching -1. So from the left, we had -1, and from the right, we had -1. And since those two things are equal to each other, then that means our limit, our answer here is -1. All right, so they have to agree in order to have a limit that exists. All right, so they have to kind of join together, kind of using that graph, even if there's an open circle there. Now we're going to do the same thing at as we approach -4. All right, so let's kind of annotate this one in blue. Here's my x value of -4 right here, right? So we're going to go, let's see, we got two different sections of graph here. Let's first start from the left. If we start from the left and we stop at -4, we can see that we're getting to 3. So from the left, we approach 3, the y value of 3. Now let's also go from the right of 4. So if I go from the right of 4, right, starting right of 4, -4, and going to it, we see we have a right-sided limit. It actually approaches a y value of 1. And since those two things, right, the limits, since the graph are not joining, the limits aren't equal to each other, we say the limit does not exist. And your reasoning here, if the question were to ask you, explain why the limit does not exist, you would say the left-sided limit is not equal to the right-sided limit. Okay, and this is actually what we call a jump discontinuity. Right, it's discontinuous, it is broken. It's almost like they have been separated and there's a giant cliff there. We call that a jump discontinuity. Now we have f of -2 and f of 4, and we can see that these are quite different. And these are different because these ask us not just what the graph is approaching, but just where is the graph at that moment? Instantaneous, right? Right at that moment, what is the graph doing? So let's just say at x equals -2, where is the graph, right? And this is kind of at an instant. So I said x equals -2. Okay, so let's just highlight that. So we're going to go back to x equals -2 over here. Let me highlight this in yellow. I'm going to go back to x equals -2. Where is the graph there? Well, there's only one point that would actually match up at x equals -2, and that would actually be this closed circle this time. So at -2 for the x, the y value is also -2. So that means at f of -2, we have -2. And notice how this one has an answer because nothing needs to agree, nothing needs to approach anything. It literally is just asking, where is the graph? And let's now check f of -4. I'm going to again highlight that. So we're going to go to our x value of -4 right here, look up, and there's only one of these points that I'm going to use. It's going to be the point that is a closed-in circle, right? We want to use the closed-in circles for these. So what is the y value associated with that? 3. So that means if we evaluate at that instant, we get 3. So another key point here is that we're looking for closed-in circles. Sorry, that was an arrow, but I don't want anybody to confuse that with a greater than sign. We're looking for these closed-in circles for these two types of problems. All right, that would mean the graph is defined at that point, and that's how we would define it with its y value. So circles don't matter for limits, just the graph and where it's going matters. Whereas if I'm asking you basically where is the graph, we need to know what y value to look for. We're going to be looking for a closed circle or the graph itself. So that's limits, and now I'm going to turn it over to you to actually answer those questions on limits. So you would have question number 2 on your own. I'm going to clear this. And you can actually look at question number 2. It's pretty similar, and just that asks you 4 questions about these graphs over here based on limits and evaluating. Now there's another question that you would be asked to solve for, and that is going to be kind of part 2 of this review series today, which was actually talking about piecewise functions. So this was actually the bulk of our work. This one takes quite a bit more time. So we have basically 3 distinct functions here. So if you were to think about this on a graph and what this were to look like, this is not an accurate picture, but you would have something like, let's say -2, and then let's say 4 over here are kind of like where the graph is separated, right? This kind of tells us the domain for each section, when to use each graph. So for anything less than -2 or anything left of -2, I'd be using like x plus 1. Right, so it might look like this, a straight line, right, all the way up through there. And then at in between -2 and 4, I would be just using the graph that is equal to 1. And then anything to the right of 4, greater than 4, sorry, between -2 and 4. Anything greater than 4, I'd be using this quadratic function, whatever that looks like, right? So it might look, you know, something, I don't know, like this. And I'm going to say again that I'm really not too sure that this is an accurate graph. I actually don't think that it is accurate. So it's really up to you to kind of just picture what these graphs look like. And this is kind of what it would look like. And now we're going to answer some questions on it. And the first question just says, find f of -2 and find f of 4. Well, this would be at an instant, right? So literally, I'm just trying to figure out, okay, if my value were -2, which function would I plug this into? Right, where would I plug -2? Is -2 less than 2? No, it's not. So I'm definitely not going to plug it into that left one. But I can see that if I were to plug in a -2 in for this x right here, we know that -2 is less than or equal to 2. Right, so that tells me that I want to be using this middle function here to evaluate and find f of -2. So f of -2. And that is going to be equal to, let's see, what is my actual function itself? 1. So actually, f of -2 is just equal to 1. There's nothing to plug in. That really just was my answer. And now I'm going to do the same thing for f of 4. And let's just see which one of these it would plug in for. Well, definitely not the first one, right? 4 is not less than 2, -2. Is -2 less than 4? Yes, but is 4 less than 4? No, it has to satisfy both of these things, right? And is 4 less than 4 here? No, 4 is not less than 4. 4 is equal to 4. So nowhere in there does it say less than or equal to 4. So there is nothing that I can actually plug into for 4. So f of 4 is undefined. And you can say that because 4 would not make any of these inequalities true. Or you can say, essentially, if you were to look at the graph, that at basically these two 4s, we have 2 open circles. Remember that open circles would be the result of less than or greater than signs, whereas a closed circle would be the result of less than or greater than or equal to. And so you can kind of start to say, well, f of 4 is undefined because there is no point that exists at an x value of 4. Right, and that's kind of what I would have for those first ones. Now I am going to clear my work here because I have to kind of scroll back and forth on a problem like this, which is unfortunate because I have so much good annotation, so many good annotations up there. I'm going to clear this, and I'm going to look for, okay, now we're going to be finding the limit as f of x approaches -2 and as f of x approaches 4, and if the limit d and e, explain why. So really we're just finding our limits here. We'll only worry about that d and e if it comes up. But right now, I just want to focus on how do I find my limits? Well, remember that in order for a limit to exist, we need the left limit equal to the right limit. And so when we set out to find the limit, we really have to find the limit of both sides and see if they join or meet up, thinking about that graph and jump discontinuities. So for this first one, -2, if you were to think of just a two-dimensional view here, we just have two x values that our graph separates at. It separates at -2 and it separates at 4. And I talked about before how to the left of -2, right, is going to be the graph x plus 1, right? So to the left of -2, we've got the graph, sorry, I got to pull up my pen again, x plus 1. And then you would see that to the right of in between -2 and 4, in between would just be an x value of 1. And then to the right of 4, greater than 4, would be this quadratic. So it's a matter of like knowing which function to use and when, depending on what the limit is asking us. So in this first one, it's asking us the limit as we approach -2. Well, we can see that -2 is actually right in the middle of two functions, right? -2 is actually kind of splitting, is right in between x plus 1 and 1. So in order to find the limit at -2, I actually have to plug it in to both of those to see if it's kind of matching the same thing from the left and right sides to see if that graph is connecting. So let me actually do that work over here. So what I would actually write here is the limit as x approaches -2 from the left, and the limit as x approaches -2 from the right. And I think our function is called f of x in each case. All right, so we're taking the limit of f of x. So now what that really just means is that we have to plug a -2 into each one, right? -2 plus 1 for the left-sided limit, right? This is the left, this is the right, is going to be -2 plus 1, which is -1. And for the right-sided limit, there's nothing to plug in, so our answer is just 1 there. And we can see that -1 is not equal to 1. So right away, we can see kind of that case here where we have a limit that does not exist because those limits are not equal. So for this number 2, I'm going to say the limit as x approaches -2 dne does not exist because the left-sided limit and right-sided limits do not agree. Okay, so, and I had to put that sentence in there because it says if the limit dne explain why. So there's my explanation. I could say something along the lines that, you know, the left-sided limit was -1 and the right-sided limit is 1. And since those limits don't agree, the limit does not exist. Maybe I should put that little bit in there. Okay, and then additionally, we have to find the limit as we approach 4. So now we can go look at our kind of number line over here and see what's happening there. At 4, we see that it's also another kind of break in our graph. So at 4, that means we can't just plug 4 into whatever one we choose. We actually have to plug it in from the left and from the right again. So we're going to do that same kind of process. I'm going to think about left and right. And how I'd write this mathematically is the limit as x approaches 4, the little negative kind of exponent there of f of x, because that's our function. And the limit as x approaches 4 in the positive direction of f of x. And now I'm just going to, once again, plug in 4 to each one of those. Well, from the left, we once again just get 1. And from the right, I've actually got to plug in, okay, 1/2 times 4 squared into that quadratic minus 2 times 4 plus 1. And let's see, we got to do our order of operations first. So exponent first, 4 squared is 16. And then we don't have any more exponents, so we're going to do our multiplication from left to right. 1/2 of 16 is 8. 2 times 4 is also 8. And we see that now we can just do adding and subtraction. So 0, right? 8 minus 8 is 0, plus 1 is 1. So we see that we get 1 on the left and 1 on the right. So since those two things are equal, that is actually our limit. So the limit as x approaches 4 is 1. Okay, and what I could say here, if I had to write this out by hand instead of typing it into the box, I would actually say, let's see, I would say the limit as x approaches 4 of f of x is equal to 1. That's how I'd write it, like mathematical notation, right? Limit notation. And then lastly, we have to identify the location of all discontinuities and classify them. Well, discontinuity happens when one of two things: either the limit does not exist, right, when we have a jump discontinuity, or we have a removable discontinuity where the limit does exist, but there's a hole there. Okay, so let me just kind of draw those in there for us, just kind of as a quick refresher. So once again, we have two different types. A jump happens when we have something like this. A removable discontinuity happens when we have, something like this, but we have a hole there. So even though the limit might exist, we might have a piece missing, and it might even have another piece kind of floating there, but it doesn't need to. And then we have an infinite discontinuity, right? And that's going to be when we have a vertical asymptote of some sort, okay, which we don't have in this case, right? There's no asymptotes in this problem, so we're really going to have one of these two or maybe both, depending. So first of all, do we have a jump? Let's just kind of take a look. Is it true that in one of these cases, the left is not equal to the right? Yes, that happened at our D&E point over here where the limit did not exist. So we're actually going to name that. So at x equals -2, there is a jump discontinuity because the left sided and right sided limits did not agree. Okay. And what I would say there is I could actually say, if I had to just write this mathematically, I could say there's a jump. And then one way to write this is why math notation is so much better sometimes, is I could say because the limit as we approach -2 from the left of f of x was not equal to the limit as we approach -2 from the right of f of x. So literally, this is saying the same thing as that, which is why mathematical notation can kind of save us sometimes. It could be even more specific than words can be. And now we have to see, are there any removable discontinuities? Now remember that with removable discontinuities, the limit does exist, but we're looking for an open hole at that exact point. So let's see, at -2, we did have, at 4 is what I want to be talking about. At 4, we did have a limit that existed, right? But was it a hole? Was it a removable discontinuity? Well, the only thing I have to do is I have to check for this open circle. Were there just strictly greater than and less than signs there? Or was there a filled in circle there, right? So all I have to do now is I have to look up, and I have to look at our 4 values. And it looks like to the left of 4, it is strictly less than. So that's going to be an open circle from the left. And we have strictly greater than. So that's going to be an open circle from the right. So that means from both directions, we're going to have an open circle, right here. So in fact, what I do have here is I do have a removable discontinuity. So we have to now justify at x equals 4. I could even say f of x has a removable discontinuity because although the limit exists, f of 4 is undefined. Okay. And that's really what I would want to say in something like that. So it's okay that the limit exists. It's just that there's no y value actually at that point to take the instant value, the instantaneous y value. So this is kind of how I'd use piecewise functions to talk about limits, to talk about defining things and actually plugging in x values. You may have to watch this section of the video 2, 3, 4 times to prepare yourself for those constructor response items, and that's absolutely okay. Go ahead and do problem number 2 on your own, which looks a lot very similar, but some different functions and some different values where we're going to be actually finding those limits. So good luck and submit that and let me know how you do.